So the last topic under operational amplifier is your different op-amp circuits. Okay, so you're going to study 5 op-amp circuits. The first one is going to be a voltage follower. Okay, second one is your integrator. Third one is going to be your differentiator. Fourth one is going to be your comparator. And your fifth one is going to be a summing amplifier. Okay, summing amplifier. So what is required in your syllabus is the circuit diagrams and the waveforms. Okay, there is no derivation. Okay, so let me start with your diagrams of your all the 5 different types of circuit. So first one is going to be a voltage follower. So in the case of voltage follower, you have the voltage from the input is given directly to the output. So V out, across the non-inverting terminal you are going to apply your input. So this is your diagram of your voltage follower. Whereas in the case of integrator, what you are going to do is minus plus. So I have omitted the supply. Okay, so here it will be V plus, here it is V minus. So integrator, what you are going to do is you are going to ground your non-inverting terminal. Input is applied to your inverting terminal. So if this is V in, so you have resistor R in. So in the case of inverter, you are going to replace your resistor RF, that is your feedback resistor, by means of capacitor. So let me take it as CF. Okay. So this will be your circuit diagram of your integrator. So opposite of integrator is going to be your differentiator. Okay, so you're going to just replace your R and C. Then it will become your differentiator. So non-inverting terminal is grounded. V in is applied across your inverting terminal. Now you're going to interchange the resistor and capacitor. So the input you are going to replace it by your capacitor C in. The feedback you are going to replace it by your resistor RF. Okay, so this is going to be your circuit diagram of your differentiator. Okay, so comparator, as we have seen in your previous video, it is an open loop circuit, right? So you have two inputs here, V1, V2 without feedback, plus this will be your output. Okay, now the last one is your summing amplifier. So summing amplifier means you are going to apply more than one input. So non-inverting terminal is grounded. Across the input, that is across the inverting terminal, you are going to apply more than one input. So for example, let me take as two inputs, V1 and V2. The output will be the sum of both the inputs. Okay, RF. So this is going to be your V out. So these are the different circuit diagrams. This is your voltage follower circuit diagram. This will be your integrator. This will be your differentiator. And this is your comparator. And finally you have your summing amplifier. Okay. So now let's see one by one in detail. So first one is your voltage follower. Okay. So voltage follower, what will be your let me draw the circuit diagram once again. So voltage follower. So in the case of voltage follower, you have your non-inverting terminal will be given the input, right? Inverting terminal will be directly given to your output. Your RF and R in are eliminated. There is no RF and R in this circuit. Since the input is given across the non-inverting terminal, what will be your gain? Gain is equal to 1 plus RF divided by R in. So these two are not there, right? So what will be your gain? AV is equal to 1. Why? What is the reason? If I apply this input across this non-inverting terminal, due to the virtual ground concept, what will be the signal across the input of your inverting terminal, it will always be equal to this signal, right? So virtual ground concept. So if it is here, it is 1 volt, the same voltage 1 volt will appear towards your inverting terminal. The same voltage is fed back, so your output also you will be getting it as 1 volt. So whatever is the input applied to the non-inverting terminal, the output also you will be getting the same signal. So I can tell that here in this case V out is equal to V in. Okay. So it is also called as buffer. Okay. Buffer. And very important application, it is used for impedance matching. Okay. So impedance matching from high impedance to low impedance circuit. So high impedance to low impedance matching. Okay, impedance matching. So this is your first circuit, that is your voltage follower. Okay, now the second one is called as your integrator. So integrator, in the case of integrator, let me draw your circuit once again. So I have told that your non-inverting terminal is grounded, your input is given across your inverting terminal. Here you have your R in. Now what is replaced here? Your feedback resistor is replaced by a capacitor CF. So this will be your V out. Okay. So what is your equation? Your equation is given by V out is equal to minus 1 by R in into CF integration 0 to T V or V in of T into dt. So this is your equation which you have to study. I will explain it to how you have got this equation. Okay, so only this is required for your syllabus. Now your output waveforms. So if I am giving an input as a square wave, okay, I'll get the output as your triangular wave. You will be getting a triangular wave. So input is square, output you will be getting a triangular wave. We are concentrating on the area of your square signal, inside the area, right? So what will be, how will you get the waveforms? So if this is your input waveform V in, okay, I am giving a square signal. So what will be your output? Output is going to be your triangular wave, V out. So here there is one more concept, since here it is input is given across the inverting terminal, output will be 180 degree out of phase, right? So if here it is positive, the output will be charging towards your what you will be getting towards your negative. Similarly, when the input is negative, your output will be positive. So your output will be a triangular wave which will look like this. Okay, so here it is positive, so you will be getting the signal towards your negative half cycle. Now here it is negative, so you will be getting the signal across the positive half cycle. This is how you get a triangular wave. Okay, now let me explain how did you get this equation. So you know that here your non-inverting terminal, the input here it is grounded, right, 0. So due to a virtual ground principle, because of negative feedback, the voltage across the input of your inverting terminal towards your amplifier will also be equal to 0. So what will be the current flowing when I apply the input here? The current I in flows through your resistor R in, and it will be flowing through your capacitor CF. So let me take this current as ICF. Okay. So at node A, if that is a node A, if I apply Kirchhoff current law, what will be your equation? I in is equal to the current flowing towards the node is equal to current flowing away from the node, ICF, right? So what will be your I in here? What is the potential difference? V in minus VA. If I take this as VA, V in minus VA divided by R in, which is equal to, what is your current ICF? The current across the capacitor is given by your rate of change of charge, right? So it is given by, what is the formula of your current? C into dV in divided by dt. Okay, so this is your what equation of your current across your capacitor. Okay, because Q is equal to C into V. Okay, this is how you have applied this equation. So what will be your V? I can take this as VCF. Okay, for your clarity. So V in minus VA divided by R in is equal to C into, what is your voltage across VCF? VCF is equal to 0. Current is through this direction, right? 0 minus V naught. So I can write that 0 minus V out divided by dt. Okay. Now what VA is equal to 0, you know, right? So V in minus, here it is VA. VA is 0. Okay. Now V in divided by R in is equal to C into minus dV out divided by dt. Okay. So I can write it as dV out. Just reconfigure it. dV out divided by dt is equal to minus, okay, 1 by CF. Let me take it as CF here. CF into R in into V in, right? Now if I have to take V out, then you can integrate both the sides. So doing integrating both the sides, what you will be getting, V out is equal to minus 1 by CF R in into 0 to T V in of T into dt. So this is your equation which you have written here. Okay. So as per your syllabus, you have to study only this final equation. This is just for your understanding. Okay. So it integrates the area of your input signal. So if it is square wave is given, you will be getting the output as a triangular wave. And what is one important property? Since the input is given across your inverting terminal, when it is positive, it charges to it, your output will be towards negative. This is how you get your integrated diagram. So next one is your differentiator. Differentiator. The opposite of your integrator is going to be your differentiator. Okay, let me draw the diagram once again. So again here your non-inverting terminal is grounded. Vin is applied across your inverting terminal. Now what is happening here? Opposite to that of your integrator means you are changing the position of your capacitor and your resistor. So here input will be given a capacitor and the feedback you will be having your resistor RF. This will be equal to your V out. Okay. Same concept. So here your final equation is given by V out is equal to minus RF into C in into dVi or V in, right? So V in divided by dt. So this is your equation which you have to study. Okay. So differentiator is similar to that of your mathematical differentiation, finding a derivative. Okay. So derivative means if you give a constant value, the derivative will be equal to 0, right? Means if you give DC, your output will be 0. AC, you will be getting spikes. So for example, if I give a square signal, I will be getting spikes here. Okay. So this output will be your spike. So it detects the AC signal. That is one of the application. Okay. So how will you get this equation? So before you have to study what is your waveforms. Okay. So your waveforms is your input. If I give a square signal, okay, what will be your output? Output V out, you will be getting spikes. Okay. So since the input is given across your inverting terminal, what will be your output? Will be 180-degree phase shift. So if it is positive, you will be getting negative spike. Okay. So here it is constant, so it will be 0. Okay. Now when the input is negative, you will be getting positive spike. Here it is constant, so you will be getting 0. Again it is positive, so you will be getting a negative spike. Okay. So it is also called as the rate of change of your signal. Okay. So derivative, this is how you get your input and your output. Now let me show you how you are going to derive this equation, even though it's not in your syllabus. So the same concept here, non-inverting terminal is grounded. So what will be your value of your inverting terminal towards your op amp, it will also be 0 due to virtual grounding. So what will be your current IF will be flowing across your input capacitor. It will take the path through your RF, right? So let me take this as capacitor. It is not CF, it is C in. Okay. So let me take the current as I in and this as IF. So what will be your, apply the same equation or same law, Kirchhoff current law across node. What you will be getting, I in is equal to current flowing towards is equal to current flowing away. I in is equal to IF. So in this case, I in is nothing but the current flowing across your capacitor. Right. So what will be your current, C into dV in divided by dt. Okay. So which is equal to, IF is equal to, what will be your potential, 0 minus V out divided by RF. So can we substitute the value for V in, D into, what is your V in? V in is equal to, VC, right? VC, voltage across your capacitor. VC is equal to V in minus 0 because the current direction is through this way. So V in minus 0 divided by dt, which is equal to minus V out divided by RF. So what we will be getting, C into dV in divided by dt, which is equal to minus V out divided by RF. Now if we have to find out what is your V out. V out is equal to minus, okay, RF C, let me take it C in into dV in divided by dt, which is nothing but the same equation which I have written here. Okay, this is how you get your differentiator output. Okay, so the next topic is your comparator, right? So comparator, let me draw the diagram once again. So the comparator compares the two signals, input signals. So non-inverting terminal, inverting terminal. If this is V1 and if this is V2, the output V out will be the comparison of the two signals. If V1 is greater than V2, output is going to be right, V1. Similarly, if V2 is greater than V1, the output V2 is higher now. So it will be in phase, that is the output will be positive. Okay, it compares the both the inputs. Okay, so in this case we are going to and also there is no feedback. Comparator is a circuit which operates in the open loop condition. Okay, so let me take the example. I am going to take in the V in, I am going to take a DC signal, that is a constant signal, and across the V2 I am going to take a sinusoidal signal. So what will be your waveforms? So if this is your V in or V1, right? V1, it is a DC signal. Now this will be your second signal V2, which is nothing but a sinusoidal signal. Okay. Now what will be your V0? V0 will be your comparison of both the signals. So suppose if this is 1 volt, okay, if here it is 1 volt, so when it reaches 1 volt, it will check here 1 volt, right? When here the sinusoidal signal greater than 1 volt, okay, now it will be your V2 will be higher than your V1. So when you have your V2 higher than 1 volt, higher than your V1, what will happen? V2 is your non-inverting terminal, so your output will be positive. Okay, so here let me make it more specific. So whenever your signal V2 is greater than V1, that is above 1 volt, you will be getting your signal to be positive. Okay, so here you will be getting positive. Remaining cases, you have your V2 to be V1 to be greater than that of your V2, right? So you will be getting a negative signal. So this is how you will be getting your signal. Okay, so this will be your V out. Okay, now the next one is going to be your summing amplifier. So what is meant by summing amplifier? Which gives the addition, okay, of two or more signals. So non-inverting terminal is grounded. Let me take the example of inverting summing amplifier. So I am going to give the input across your inverting terminal. So it is summing. So more than one input is applied to your inverting terminal. So if this is V1, if this is V2, let me take it as R1, R2. So in this case I am going to take all the resistor as equal. So what will be your V out? V out will be equal to, since the input is given across the inverting terminal, there will be 180 degree phase shift, minus of V1 plus V2. This is going to be your output equation. Okay. So for example, how will your waveform look like? So if I am going to add two signals, let me add a square wave and a sinusoidal wave. So here in this case I am going to give a square wave, and here I am going to give a sinusoidal wave. Okay. Now what will be your input signal? V1, I am taking it as a square wave. So if I take as a square wave T, and V2 if I take as a sinusoidal signal. Okay. So how am I taking? So I am taking a, goes on like this. Okay. Sinusoidal signal V2. Now what will be your output? Output will be the sum of both the signal. Okay. V1 and V2. So both will be added together. Okay, listen here very carefully. So here in this case, this is your 0 point, right? 0 point. So if this is equal to 1 volt, now this signal will be 1 volt will be added with this signal, right? So since the input is given across the inverting terminal, the output is going to be 180 degree phase shift. So if it is positive, you will be getting the output in negative. So this 1 volt will be added to this. Means your 0 will be now shifted. It will be shifted to your DC level. So since your output is negative, it will be shifted across your negative half cycle. Now 0 will go to minus 1 volt. So you will be getting the signal just like this. Okay. Now whenever you have here transition, you will not get a signal. Okay. So this will be your transition period. Again, when your input is negative, you will be getting your addition in the positive side. So this will be your signal. Okay. So it goes on in this way. Okay. Averaging. So how did you get this equation? So what will be a working principle? When I give here V1, the current flows here, I1 flows here through here, I2 flows to here. Since your non-inverting terminal is in 0, here also the input will be 0 due to virtual ground. Now the current will take this path. So this will be your current in the feedback, IF, I can tell. So now what will be your equation? I1 plus I2 is equal to IF, current flowing towards is equal to current flowing away. So similar to that of the previous equation, if we write I1 is equal to, what will be a potential? V1 minus 0 divided by R. What will be your I2? V2 minus 0 divided by R. What will be your IF? 0 minus V out divided by R. So since R is equal, we can cancel all the R. So finally we will be getting V out is equal to minus of V1 plus V2. Okay. So these are the different circuits of this op-amp configuration. Op-amp circuits. By this your op-amp section is complete.